let's dive into simple electricity. So now we will make some very basic introductions and introduce some fundamental concepts. So what can be more fundamental than the building block of all matter, and that is an atom. So the most simple atom is hydrogen atom, and that consists of a positive nuclei, which in its term consists only of a single proton, and electron, negatively charged, which orbits this proton. So we have some electrically neutral system, atom, and elementary charge of electron is minus 1.6 10 to minus 19 coulomb. The charge of proton will be the same, it's just different sign. So it is important to highlight that electron in an atom as a quantum system cannot possess any energy. So its energy is predefined by quantum effects. So it can occupy only defined orbits around this nuclei. So we have some ground state n equal 0, some excited state first n equal 1, then a second excited state, and so on. So now, when we want to study electricity, we need to deal with some materials, and these will be different materials, and usually we deal with solid state materials, so not with just isolated atoms. So what will happen when we start to put many atoms very closely together? So they will start to interact with each other, specifically their electronic orbitals will start to interact, and this will result in creation of, instead of isolated energy levels, we will form in such well-packed structure some bands, so-called. It's a bundle of energy, the same energy levels originated from all atoms which are introduced into this system. So let us assume that we have capital N atoms, and now these n atoms, each atom will contribute a single energy level to different bands. So we will have some capital N energy levels in one band, then there will be capital N energy levels in another band, and so on. The thing is that as we have multiple energy levels available in atoms, we will have multiple energy bands, which represent kind of group of the same energy levels from all atoms included in this solid state material. However, in terms of electrical properties of the material, what matters, that is only valence and conduction band. So valence and conduction band. Valence band is called because it's formed by energy levels of valence electrons. Those are the electrons which under ground state occupy the highest energy levels. And then conduction band will be formed with energy levels which are not like higher energy levels, which are not occupied under normal conditions. So we have kind of field with electrons valence band and empty conduction band. And this gap here is a gap of forbidden energies. Here there are no energy levels allowed from quantum principles in atoms which form this solid material. So here will be some gap, will be or will not be, depends on type of atoms which form the crystal structure and crystal structure itself. So this gap will actually have a very strong dominant effect on electrical properties of solid state material, which we form by putting multiple atoms together. So let us look closer into this specifically interesting for us valence and conduction band in order to make our life a bit easier, since we don't need to consider any other energy bands at this point. So in order to make it more representative, I have a few samples. So here is aluminum foil, here is piece of silicon wafer, and here is some plastic tube. So we can classify these materials as metal, semiconductor, and dielectric. So now, what is the key difference between these type of materials which possess very different specifically electrical properties? So the thing is about metals that top of the valence band is higher or equal to the bottom of the conduction band. Means that they overlap. And what it means in terms of electrical conductivity, let's ask this question in terms of available free charge carriers which can move along the conduction band. They are always there, so they no matter at which temperature, since they overlap, we always have some electrons negatively charged which are delocalized in crystalline solid with metal properties as defined as metal, and once we have some external field, they can electric field, they can move and participate in charge transfer. So in order to demonstrate this, we can actually do some measurement with a multimeter. Let's put to range to 20. Let's go to the lowest range here, which is 200 ohm. So now if we place the electrodes, we see that it shows us what, 5, 4, 3 ohm, depends, actually it's actually 0.1 ohm. So we see it's a short circuit, because if we make a short circuit with these tips, then we see also such very low values. That tells us that electrical conductivity of aluminum foil is very high. It's expected because this is a metal, valence and conduction band overlap, so this material provides very high electrical conductivity. So now semiconductor. In case of a semiconductor, these conduction and valence band don't overlap anymore. For actually that is wrong. Let me correct this. So let's keep the color the same. So we have bottom of the conduction band, and here is top of the valence band. So you see these guys do not overlap anymore, and here we have some gap, which is our energy gap, and for semiconductors it's in the range larger than 0, so we have some gap always, and it is smaller than 3 electron volts. It's some rough estimation, but we can stick to this 3 electron volts. So in this case it means we do not have free electrons in the conduction band. In order to move electron from valence band to conduction band, so we have some free electron here, and automatically we get free positive charge called hole in the valence band. Both of them can move in electric field in opposite direction. So let's say if electric field is in this direction, then hole will move here, and electron in opposite direction, since they have different charges. So hole is just absence of electron, and it can be considered as a charged particle moving in valence band. So now, in order this to happen, we need to provide some energy. It's thermal energy, vibrational, like vibration of crystalline lattice in semiconductor, or it can be some photo excitation, absorption of a photon as a quant of light energy. So now let us check this in terms of electrical conductivity. And by the way, this is silicon wafer, so band gap of silicon is equal to 1.12 electron volt. So you see this value is in the range for semiconductors, and that's why silicon is a classical semiconductor material. So let us now try to measure its resistance. Like between these two electrodes, we see there is nothing. No signal are shown on the multimeter, and that is actually because the range is at 200 ohms. So if we switch it, let's say to 200 kilo ohms, let's try again. Oh, you see there is some current flowing through the sample, so we can measure. Let me go maybe to like 2 kilo ohm. Let's see what we get. Well, 2 kilo ohm is too low, and we can stay with 20 kilo ohm. Yeah, here we see the resistance. It's somewhere in the range between 1 and 4 kilo ohm. Of course, it changes quite a lot because we don't have good ohmic contacts. So I just press this metal tips terminals of the multimeter, and it doesn't form good ohmic contacts to a semiconductor material. So you need to take care for high quality ohmic contacts, then these readings will be stable. But this simple experiment can show us that indeed semiconductor material can conduct electricity, but its electrical resistance is much higher in comparison to metal. So we will quantify electrical resistance a little bit later, and resistance in general, but now it's a simple example how we can classify different materials. So we considered metal and semiconductor. So now if we look at dielectric, we will have the following picture. So it will also have gap between valence and conduction band, but the difference between semiconductor will be just that this gap will be much larger. So EG will be larger than 3 electron volts. So in this case, it's still possible to do the same procedure, excite electron from valence band to conduction band and create free charge carriers, but it will require much more energy than semiconductor, and that's why at room temperature or even at very high temperature we will probably melt the electric material or burn it before we reach high enough temperature to excite free charge carriers which can participate in charge transport in the semiconductor. So that's why dielectrics do not conduct electricity. And here we have some example. I just found some plastic tube. So it's a solid state material, but let's check its electrical conductivity, like electrical resistance. We see there is no signal, means current doesn't flow through this material. Let's go to the maximum range, so 20 mega ohms. Let's check 20 mega ohms. So you see there is no current, means that resistance of this material between the tips of the multimeter is larger than 20 mega ohm, which is quite large value of electrical resistance. So dielectrics, because they have very large band gap, do not create conditions for free charge carriers, and thus cannot participate in facilitate some charge transport through this type of materials. So that's why we have metal, semiconductor, and dielectrics, and that's the type of materials and their combinations which are commonly used in all type of electrical experiments and devices. So let us remove these samples for now, which I hope were useful for some demonstrational purpose. Clean this board, and now we will give some introduction of quantitative parameters which can describe charge transport in a conductor, solid state conductor. So we mentioned that there are positive and negative electric charges. So where is electric charge? There is electric field. So electric charges create electric field, and it is agreed that we depict electric field with electric field lines, and they originate on positive charges, and the electric field lines terminate on negative charges. So if we place a positive electric charge in external electric field, then there will be some electric force exerted on this positive charge. This is our electric force. Since force is a vector quantity, so its orientation will coincide with orientation of the electric field line for positive charge. If we place here negative charge of the same magnitude, then we will have the same in magnitude but opposite in orientation electric force exerted on negative charge. So now, if we have mobile charges and create some electric field around these mobile chargers, obviously they will move with certain velocity, which will be compromised between exerted electric force and scattering of these charges in the material. So there will be some equilibrium, so-called drift velocity. So they will move with certain drift velocity through material. So let us consider some metal. We know that metal, by definition, because of its energy structure, that valence and conduction band overlap, always possesses multiple free electrons in the bulk of the material, and we can describe their density with N, which is in units is 1/centimeter cube. How many electrons per cubic centimeter, spatial density of electrons in metal. We know that electron is a carrier of elementary charge Q, which is equal, I refresh, you already mentioned it a little bit earlier, 1.6 × 10⁻⁹ Coulomb. And how we define electric current density, which is J. So that is equal to elementary charge Q times N times V drift. So these charges will move with some drift velocity along metal, because we create inside metal some electric field. Units for current density, that is ampere per square centimeter. So if we need to go to current, we just multiply current density by cross-section area A of the conductor. So now, how do we represent this drift velocity? Because that's just characterizes how fast electrons are moving in the direction of electric field, but it doesn't describe some properties of the material in which this transport is happening. So we can introduce so-called mobility of electrons and or general mobility of charge carriers in this given example, electrons in the material. So it describes how easily electrons can move through the metal. Units for mobility, this will be centimeter square over volt times second. So now we can represent VD, drift velocity, as product of mobility and electric field. So if we substitute it here, so for current density, we can write Q times N times mu and times this electric field, which drives charge carriers. So now we can look at these three parameters, and here what we see, Q is elementary charge, N and mu, concentration of electrons and their mobility in given metal. These are properties of the material. So we can represent it. Here we can write again for current density that it's equal to sigma times electric field, and that is our sigma. So this is specific electrical conductivity, sigma, and we can represent it also as electric field divided by rho, which is specific electrical resistance. So specific electrical resistivity is represented in units ohm times centimeter. So this sigma and rho, which are specific electrical conductivity and specific electrical resistance, these are characteristic of the material, and That's the quantitative way how we can describe how well this material can conduct electricity. So now one more parameter we need to introduce today, and that will be the last thing we do in the scope of this discussion. So that's electrical resistance. So let us assume that we have a metal rod with some length L, cross-section area A, and specific resistivity of the material ρ. So if we measure resistance between this and these edges of the metal rod, what electrical resistance will be. So that's actually what we did with multimeter previously. We placed it between 2 points and measured electrical resistance between these 2 points. So in this case, we can introduce electrical resistance as R, and that is equal to product of specific electrical resistivity times length of the sample divided by cross-section of the sample. So now, if we look at the units, we will see that units for electrical resistance is ohms. Or it can also be represented as this Greek letter. So that is the very basic introduction to aspects relevant for electricity, which I wanted to discuss in our first lecture. So we will continue next time. If you're interested, please follow this channel. I will add new lecture with further discussion of connection of resistors and with some practical demonstrations for better understanding in the near future. Thank you for your attention and goodbye.